Hi, this is Rishabh Pandey, and I am a physics faculty at askIITians. Right. So today we are going to talk about the third lecture of the chapter, that is Human Eye and the Colorful World. Please make sure that you have watched all the previous videos just to make your understanding much more clear. Otherwise, if you haven't watched it, please go and watch it first. Right. If I move forward with this topic, I would rather say that this will be basically covering about the aspects of prism. In this topic we are going to cover about the topics such as applications of spherical mirrors and lenses, right? Why do we use them? What are the benefits of using them? Then refraction of light through a prism, and then the dispersion of light. These three topics are going to be covered today. I hope every one of you is familiar with the spherical lenses and the mirrors. As you can see over here, this is a mirror, right? And you can see these kinds of mirrors on the turnings on road. Turnings of road. Generally, these kinds of mirrors are used at that places. The benefits of using these kinds of mirrors are very simple, because you can know that which vehicle is coming or whether a vehicle is coming or not. This thing can be easily predicted by using these kinds of mirrors, right? Similarly, we have different kinds of lenses which will be used, and will be covering all those aspects today in this lecture. So what we are going to start with the application of spherical mirrors and lenses. Let's start with the mirrors first. As I told you earlier, this is a kind of mirrors. Now, if I move forward, just to give you a brief snap of what all things we have covered before. If I talk about spherical mirrors, spherical mirror, then and lenses, in fact, and lenses. So there are two types of mirrors and lenses, right? Say the first kind of them is convex, and the second kind is concave. Say if I have a mirror like this, which is a bit curved, you know, with this as a silvered portion and this as a reflecting surface, right? So say a ray of light is falling on it and then getting reflected back. This is a kind of concave mirror. If I talk about convex mirror, then it looks like this, with this as the silvered portion and this as the reflecting surface. Say a ray of light incident on it and then again getting reflected back, right? So this is a kind of convex and concave mirror. Similarly, if I talk about concave and convex lenses, then I hope you can predict. Say this is a kind of yes, so this is a kind of concave lens. Concave lens. Say if I have a ray falling on it like this, right, and getting diverged like this. So this is a phenomena of refraction, because the ray is not bouncing back, but instead it is taking a curve and going in the other side, right? Similarly, if I draw a convex lens, then it should look like this. Although I'm not that good with the drawing, so please bear with me. Say if I have a ray of light incident on it and it gets converged like this, right? So this I can say that this is a kind of concave lens, whereas this is a case of convex lens. This is convex mirror and this is concave mirror. See, there are different uses of these kinds of mirror, isn't it? There are different uses of these kinds of mirrors. Say, for example, if I want to, if you could recall, if I want a kind of image which is real in nature, which is real in nature, and give you an inverted situation. In that case, we should be using the concave mirror, right? Similarly, if I want, just give me a moment. Yeah, if I want a kind of mirror which is like which gives me an image which is barely virtual, it should be laterally erect, it should be erect instead of inverted. So if I need those kinds of images, then obviously I will be using a convex mirror, right? So there are different kinds of mirror for different kinds of uses. It depends upon the person to person. Like for example, if I need to see this, say this is the side view mirror. Now for by using a side view mirror, if I want to find a kind of see a vehicle which is behind me, and if I want to see that, in that situation I should be using which mirror? See, if I will be using, see, you should be clear na, that I have to use a mirror, not a lens in this case. Now, if I want to see the vehicle behind, I cannot, the options are plane mirror, the options are convex mirror, and the third option is concave mirror. You should be clear with your ideas, right? Plane, convex, and concave. Now, for if I am using a plane mirror, obviously the benefits of using a plane mirror is that I'll get an erect image of the vehicle. But the problem with the plane mirrors are that I will be getting a kind of image which is of the same size of the object, same size. Try to understand that. Let's say that there's a truck behind me, and I want to see that truck, right? And there's a bike behind the truck, right? You are driving, you are on the driving seat with your side view mirrors on, and at the back you have a truck, and behind that truck you have a bike, right? The whole space will be occupied by the truck itself or a plane mirror. You won't be able to see the bike. But is that the case? No, probably no, right? Because by using a side view mirror, you can easily look at the truck, the car, the bike, everything which is lies behind that. That means the truck is not basically occupying the whole space of the mirror. So the drawback of using a plane mirror, is that you get to see the images which are of the same size of the object. And if say the object is very large, it will cover the space for those smaller objects, which is a kind of bit issue, isn't it? So plane mirror could be an option, but it's not that great option, isn't it? So okay, let's cancel this out. If I use a concave mirror, and let's go to concave mirror first, and then I'll get back to the convex. The drawback of getting using a concave mirror is, the first drawback is that the image will be inverted. And the drawback of basically using an inverted image is, see, you have some vehicles behind you and you are seeing an inverted image of those. The drawback is inverted. The image is inverted. So if it will be an inverted image, you just try to imagine that there's a truck or a car or a bike behind you, and the image which is being formed on the mirror is inverted. That means the tires are on the top and the roof is at the bottom. Won't be that weird, isn't it? So size is not an issue, and generally in a concave mirror, but acha, okay, let's talk about this. It makes image of a large size when nearby. So say there's a vehicle which is very close to the mirror. It will form a very large image, again occupying the space of the other vehicle. That means concave mirror is not at all a not at all a good option, whether if you talk about the inverted situation, whether you talk about the size situation, right? So we cannot be using the concave mirror. But if I talk about the convex mirror, basically if you see, convex mirror has addressed both of these issues. It has addressed the issue of the size, and it has also addressed the issue of the inverted images. See, for a convex mirror, the case of a convex mirror, it's erect, the images is erect, and the image is of the small size, right? If I say this is the benefit of using convex mirror, so the point is that we should be using convex mirror. And why should we be using this? We just proved it, right? If I move forward to the other kind of cases, that is use of concave mirror, as you can see, if what are the uses of the concave mirror? The first is the concave mirrors are used in some telescopes, right? Why we use a concave mirror? Because the object, when the object is very large very large, and I want to find a very small object of image of it. In that situation, concave mirror is kind of good option, isn't it? If you remember, just give me a moment. Yeah, if you remember, say if I have a concave mirror, you know, this is a concave mirror with this as the silvered part, and the principal axis basically lying like this, this is the principal axis, and there's a ray of light from an object which is quite far, which is a very quite far object. Say this is the first ray of light. It comes and then it goes like this, right? Similarly, another ray of light falls on it. If I am using, let me use by this by another color. So there's a ray of light like this, goes like this. That means the image will be formed over here. And will the image be of a very small size? Like for using a telescope, when I'm using a telescope, what I have, the object is nearly at infinity, and it's very large. So if I use a concave mirror, I'll get a very small image of the object, right? So the point is small size of infinite object, small size of the infinite object. So if I'm using a concave mirror, this is a very first benefit, right? They are also used to provide magnified image of the face of a you want to have a very close look at your face. In that situation, plane mirror is not a good option because it will obviously form the same size. Right. So right. So this, as you can see, that the image which is basically found over here is quite enlarged. If I try to form a situation like this by using a concave mirror, then basically it looks like, and say this is the principal axis, and the object lies very close to the mirror. Say this is the object which lies very close to the mirror, right here. The rays which are going to be formed in this case is a ray traveling like this, going like this. right? And there's a ray which goes like this and then again goes like this. That means this will always form a virtual image when the object is very close to it. And see, if I extend it like this and then it like this basically forms an image over here. If I talk about the properties of this image, this image is erect. That means it's a virtual image, it's enlarged. So this is what they are trying to talk about. That they also provide a magnified image of the face for applying makeup. So this is like a kind of very nice thing. And then this is used by dentists to same case that if the dentist want to see something behind the tooth or something like that for very small issues, and obviously he can use a concave mirror by bringing that mirror close to the teeth. It will form a virtual image which will ultimately form a very enlarged image, right? Then it is used to see large size of the image. Obviously, the same thing has been written over here, right? Can you now understand the uses of the concave mirrors? So here we were basically talking about the uses of the convex mirror and the concave mirror. है ना? Beyond this, if you go for the uses of the convex lens and the concave lenses, they have different uses depending upon the situation, as in this case, right? Now, going to the next thing of our topic, that is refraction of light through a prism. Refraction of light through a prism. I hope you must have seen this diagram, all of you. है ना? That let's say there's a ray of light, white light, and a white light getting over here, and then deviating and then forming 7 bands of colors like this. And 7 bands of colors like this. Right? Basically, a vibgyor will be formed in this situation. This is the situation of the mirror. Now, how is it basically useful and what all things has been written over here? Let's try to discuss this. Say if I have a light which is basically passing through here, then this will be the normal, and say this will be the angle of incidence. So this will be angle I. This is correct, and then this light is again getting refracted out of it. So this will be like angle of, say, let's say if this is R dash, and this will be the emergent angle. So this will be E, or you can also write it as I dash. In some book, you'll find this as written as angle I dash. Now, if I connect these two, and basically this ray was supposed to go like this, but it went like this. That means this ray basically deviated by this much angle. If you could understand. So this is the angle of deviation as written over here. Angle D as the angle of deviation. These are the angles. So basically in a prism, what I'm trying to say, that in a prism, there are 4 angles which needs to be discussed. Angle of incidence, angle of refraction, angle of emergence, and this angle R dash as well, right? And obviously the angle of deviations. So these 4 angles are needs to be discussed in this situation. Let's say, and yes, of course, the angle of prism as well. The angle of prism. What's the angle of prism? See, angle of prism is basically the property of the prism, and then the property of the prism of deviating a light, that how much it can deviate. Say if I go to the formula segment, let me erase this thing and let me re-explain it. The situation, right? This is the situation, and yeah, this is the ray of light, angle I and I. Suppose, see, basically this was supposed to go like this, but it didn't went like this. So point is that, say, this is the first point where the deviation basically occurred. So let's take it as delta 1. And if I extend this, basically this was supposed to go like this, but it went like this. So that means this is delta 2 and this is delta 1. Right, this is delta 2 and this is delta 1, and combining these two, this is like delta, which is basically a combination of delta 1 plus delta 2, isn't it? See, there are 2 points where this array was supposed to be deviated, right? So here it was like deviation, the first deviation, that's delta 1, the second deviation is delta 2, and the sum of the total deviation, that is delta, where delta is equal to delta 1 plus delta 2. Am I clear? Now if I extend this, so this will be written as delta is equal to delta 1 plus delta 2, delta 1 plus delta 2, where basically delta 1 is what? If you could, this is angle I and this is angle R. So basically this was supposed to be equal to this. That means delta 1 can be written as I minus R. Clear? Similarly, delta 2 can be written as I dash minus R dash, the one I just explained, the I dash and R dash concepts, right? And if I solve this, this basically become equals to I plus I dash minus R plus R dash, correct? And see, if I extend this, and there's one more thing, if I extend this, if I extend these two normals, they meet at a point, and the angle at which they meet is the angle theta. So that means these two normal, if they are extended, they meet at an angle theta. And by the concepts of congruent triangle, it's like R plus R dash plus angle theta is equal to 180 degree. See, R dash, and see this is angle theta, and this basically forms a triangle, isn't it? As you can see, this forms a triangle. This is R dash, and then this as angle theta. So basically this forms a triangle. As you can see, triangle E, then say this is O and this is F. Triangle EOF forms an angle, combines an angle triangle which basically has the sum total as 180 degree, and A plus theta is equal to 2 pi minus pi exterior angle, and this exterior angle concept, right? If I combine all of these, from here I can say that R, from here I can say that R plus R dash is equal to angle of prism. What is angle of prism? The deviating power of that particular prism, and it depends upon the material of the medium, material from which the prism has been made of, material of prism, right? So this is what I can conclude from here. And if similarly, if I put this as over here, I'll say that deviation is equal to I plus I dash minus A, correct? So here basically we have the formula of, if I want to find the angle of deviation, this formula can be used, correct? Or instead of this, you can also use it as the formula, that is delta is equal to mu minus 1 into A. These are the two formulas by using which I can find the angle of deviation. Angle of deviation. If I move forward, I hope I'm clear till this part. Right. Now, this is basically the dispersion of light. And what's dispersion of light? The splitting of white light into its constituent particle is called as dispersion of light. Although we'll have a much more detailed discussion on this in the next topic, that is deviation of light. And when we'll be discussing that, we'll have a much more discussed way. But still, as you can see that, say this was like a normal, and this, there was a normal over here. The light got disparate. If I say which light has been least deviated, so the least deviation has been made by red color, and the maximum deviation, as you can see, the maximum angle of deviation, so it's like maximum deviation, has been made by violet. Basically, violet is responsible for the maximum the light which is basically maximum deviated, and red is the light which is least deviated. And this phenomena of splitting of white light into its constituent colors is called as the dispersion of light. So a white light getting dispersed into its 7 constituent colors. Correct? Now the question basically arises that why this thing happens. What basically the prism does, that a white light coming entering into a prism, and then when it comes out, that white light gets deviated into its 7 constituent color. The answer to this question basically lies in, just give me a moment. The answer to this question basically lies in the wave theory. Wave theory. Wave theory of light. Although you'll have a much detailed discussion on this topic in class 12, but I'll just try to give you an idea. Wave theory is what? Say basically, if I have a ray of light, see basically a ray of light, every light has got its own wavelength. As you can see that we have the spectrum of light. So there's a visible region. Visible region. What's the visible region? Visible region is that particular region in which the light falling in that particular wavelength is visible to us. Anything beyond this visible region, not visible. And anything again less than this visible region is again not visible. So what's visible is only this spectrum of light. So wavelength, it depends upon the wavelength. Depends upon the wavelength of light. If a light has some wavelength, then it's obviously visible to us. So I'll just give you an example. For one particular color, there are various shades of the color. Say, let me draw this here. This is a blue color, as you can see. This is also a blue color, and this is also to an extent is a blue color. Now, point is that all these three are blue colors, but all of them are a bit different. The starting with it's a bit lighter one, then followed a bit darker one, and then a more darker one. Why? Because there's a wavelength for every color. So as the wavelength changes, let's for example, I'm just assuming that this color has a wavelength of 400 nanometer. Suppose it's not the exact value. I'm just trying to explain it. Just try to understand it by considering it as an example. So this has a wavelength of 400 nanometer. If I decrease the wavelength, the color changes. Say if I have decreased the wavelength and I have made it to 395 nanometer, the color will change. Although it will remain blue, but it will be, let's say, a bit lighter color shade of the blue. And then say if I have again decreased it to 390 nanometers. So this is like the 390 nanometer, and this is like the 395 nanometer. Point is that if I just change the wavelength even by 1 nanometer, the color basically changes. The shade of the color basically changes. So the color light has, all the lights has their own wavelength. All the lights have own wavelength. Yes, all the lights have their own wavelength, and the wavelengths are basically are the identity of that light. Now, speed of different light, and speed of light is different in different medium. So if I change the medium, the speed of all the lights changes in different medium. As you can see that generally in air, they all have the same speed. So here when the white light was basically entering, it was air over here. The white light entered. But white light is a constituent particle of all these 7 colors. So as soon as the medium changes, this is now medium 2, right? Medium 2, which is glass, right? So as the medium changes, this white light splits into 7 different colors, right? Followed by here to here. This white light splits into 7 different colors. So splitting of white light is because of the fact that every light has their own wavelength. I hope I am clear till this part, right? Dispersion of white light is yes. What's the dispersion of white light? When a white light basically enters from one medium to another, the speed changes, and due to change in the speed, they basically deviate into different angles, with having their own angle of deviation. If you look at this first question, it says that a student traces the path of a ray through a glass prism in 4 different values of angle of incidence. On analyzing the diagram, he is likely to conclude that the emergent ray. See, if I have a prism like this, right, and a student traces the path of a ray through a glass prism for 4 different values of angle of incidence. Say this is the first angle of incidence, first ray of light, then followed by yes, the second angle of incidence, then followed by this is space issue, but still I will somehow try to manage. So this is the third angle of incidence, right? They will have their emergent ray differently. Let's say this has its own different emergent ray, this has its own emergent ray. Point is that is always parallel to the incident ray. Is always parallel to the incident ray. Is it ever possible that the emergent ray is parallel to the incident ray? I don't think so. I don't think so that this is possible. Is always perpendicular to the incident ray? No way, right? It's always parallel to the refracted. Still no way. It always bends at an angle to the direction of the incident ray. Yes. So try to analyze all the options and then choose the correct answer. Next, in the following diagram, the path of ray of light passing through a glass prism is shown. In this diagram, the angle of incidence, the angle of emergence, and angle of deviation respectively are. See, here when this light basically entered, so this entered at an angle with the normal. So y will be angle of incidence, right? Then what they are asking angle of incidence is this angle of emergence. See, when this ray went out of it, this is the normal, and this is the angle which it has made, right? This is the angle which it has made with the normal while moving out of the prism. So now the Q angle will be your angle of emergence, right? Then the angle of deviation. See, this ray was supposed to go like this, but it went like this. So the angle of deviation would be this. It was supposed to go like this, but it went like this. So this basically, this angle will be the angle of deviation. So here P will be angle of deviation. True. P will be the angle of deviation. So if I talk over here, then yes, the angle of incidence y, q and p. This option D will be the true. Right. I hope you are getting this. Moving forward, they have asked that on tracing the path of a line, the student mark the angle of incidence as shown in the figure. The correctly marked angles are. Okay. See, this is try to pause this video and solve this question by your own. So now this will be the angle of incidence. Yes, absolutely true. This is how he has marked angle of deviation. Is it true? No, I don't think so. Angle of deviation is wrong. Then this is the angle of emergence. Yes, angle of emergence is true. But r, is this the angle of refraction? No. Basically what he has done is he has interchanged d and r. So that means d and r are wrong, I and e are correct. As you can see, I and e is the correct option, right? Now look at this question. Find the value of I, r dash, it's not, it's r dash and I dash, and the angle of deviation. That's okay, fine. Say what they have said is we are supposed to find the angle of incidence, angle of reflection, angle of this refraction, and then angle of I dash, or you can also say it as angle of emergence, and the angle of deviation, right? Let's proceed first. See, basically there are, say this is the ray of light entering, and then emerging. When basically this ray has entered, it entered from one medium to another, right? It was supposed to go like this, but it went like this. True. So it was supposed to go like this, and this is the angle of incidence as shown in the figure. This is the angle of incidence, and this will be the angle of refraction. And how to establish a relation between angle of incidence and angle of refraction? Yes, the first, if I talk about the first thing, that is angle of incidence. Find the value of angle of incidence. Angle of incidence is, we'll talk about it. See, for the angle of refraction, sine Snell's law will be used, right? That is mu2 by mu1 is equal to sine this angle. It will be mu2 by mu1 is equal to sine r by sine I. True. Mu2 in this case is mu2 for a glass. You should have this thing in mind that for a glass the refractive index is always root 2. So it's like root 2 over here divided by 1 because it's air, na? So it's like 1. Sine r I need to find, and sine I is sine 45. So sine r will be, see, 45 will be root 2 will be 2, and sine r will be, I mean, it's like root 2, and this it will be root 2 is equal to 1 by root 2. So this root 2 will get cancelled out, and sine 45 and root 2 will get cancelled out, and so sine r is basically coming out to be, 1. That means angle of r is 90 degree, isn't it? So angle of refraction is 90 degree. If I proceed further, the angle of what they have asked, r dash. Yes, r dash. They have asked to find the angle of r dash I and I dash. If you look at the previous relation, it was that r plus r dash is equal to a. True. What's r? 90 degree. R dash I need to find, and a in this case is 60 degree. True. So the angle of r dash will be minus 30 degree. So this will be the angle of r dash, and this will be the angle of I dash. So r dash will be 30 degree. Correct? If I talk about angle of emergence, can the Snell's law be again used in this case? For the third situation, can the angle of emergence be again used in this case? That is mu2 by mu1 is equal to sine r dash upon sine I dash. Mu2 is, in this case, mu2 will be 1, isn't it? The light ray is entering into the air, isn't it? So the mu2 in this case is supposed to be 1, and mu1 will be root 2. R dash will be that sine 30, correct? It's like sine 30 degree, and sine I dash I need to find, so it's just sine I dash. So sine 30 is 1 by 2, correct? And if I solve this, then I'll get the value of sine I dash will be 1 by root 2, which means I dash will be 45 degree. 45 degree. So yes, R dash, I is like 45 degree, na? So I is 45, I dash is also 45, and R and R dash we successfully found. But if I talk about the fourth one, that is the angle of deviation, again by using that same relation which we discussed in that particular slide, I dash angle of deviation can be found by using the relation delta is equal to I plus I dash minus A. True. I is what? 45. I dash is also 45, and prism angle is 60 degree. So if you solve this, you will get the value is 90 minus 60, that is 30 degree. So 30 degree will be the angle of deviation. That means the light has deviated by an angle of 30 degree. Are you getting this? Right. Right. So basically, in this session, we discussed regarding the applications of mirrors, the application of convex mirror, the application of concave mirror, then refraction through a prism, the concepts of deviation, angle of prism, angle of incidence, angle of refraction, angle of emergence, everything, and then dispersion of light, and what is the reason for the dispersion of light, and these are the various questions related to it. Right? Chalo, I'll see everyone in the next session. Bye bye. Take care.